Good morning, student. How are you? In this session, we will take numerical on design of wall spring. The speciality of this problem is the spring index C is not given. You have to take special efforts for calculating the spring index. Let us have a problem. It is desired to design a wall spring for IC engine with the following details. First, spring load is equal to 80 Newton when valve is closed. In this condition, W1 is given when valve is closed. The value of W1 is equal to 80 Newton. Second, spring load is equal to 100 Newton when valve is in open condition. Means in this condition, means W2 is equal to 100 Newton. Third, the space constraints for the fitment of spring are: inside guide bush diameter equal to 24 millimeters, means DI is equal to 24 millimeter. Outside recess diameter equal to 36 millimeter, DO is equal to 36 millimeter. Fourth, wall lift is equal to 5 millimeter, delta is equal to 5 millimeter. Spring steel has following properties: ultimate tensile strength equal to 700 Newton per mm square, means SUT is 700 Newton per millimeter square. Modulus of rigidity, that is G, is equal to 8.4 into 10 raised to 4 Newton millimeter square, that is G is equal to 8.4 into 10 raised to 4 Newton per millimeter square. 6. Spring ends are square and ground. 7. Permissible shear stress for spring wire, that is equal to 0.5 SUT, means tau P is equal to 0.5 into 700 Newton per millimeter square. So TP is equal to 350 Newton per millimeter square. Now determine first wire diameter small d. Second, spring index C. Total number of coils N dash. Solid length of spring, that is LS. Free length of spring, that is LF. Pitch of coil, that is P is required when additional 15% of working deflection is used to avoid complete closing of coils. So this is about the problems and data required and data given. Now we will list down formula used. Capital D is equal to, or mean coil diameter D is equal to DO plus DI upon 2. Tau is equal to K, that is Walsh factor, into 8W2, means maximum load, and mean coil diameter D upon pi D cube. Or in terms of C, this formula tau is equal to K into 8 into maximum load W2 into C upon pi D square. C, spring index, is equal to capital D upon small d. Walsh factor K is equal to 4C minus 1 upon 4C minus 4 plus 0.615 upon C. Delta is equal to 8W D cube into N upon GD raised to 4, or delta in terms of C, that is delta is equal to 8WC cube into N upon G into D. N dash is equal to N plus 2, as spring is square and ground end. LS is equal to N dash D. LF is equal to LS plus delta maximum plus in the bracket 0.15 into delta maximum. Pitch is equal to LF upon N dash minus 1. These are the list of the formulas. Now we will solve the problem. Wire diameter. First we will determine wire diameter. Mean coil diameter is equal to 36 plus 24. From this formula, DO is equal to 36 and di is equal to 24. From this we will calculate mean coil diameter. So mean diameter comes out to be 30 millimeter. Now as spring index is not known, take k is equal to 1. Now from this formula, transferring d on left hand side and other values on another side or right hand side, this formula becomes like this. Now putting the value of tau, k, W2 and D, the D comes out to be 2.79 millimeter. Now we will take 3 millimeter increased value for the sake of Wahl's factor. Now D comes out to be 3 millimeter. Now we will calculate the spring index C as the value of mean coil diameter is known and wire diameter is known. So we will calculate C, that comes out to be 10. We will calculate the Wahl's factor K, putting the value of C is equal to 10. So K comes out to be 1.145, that is the Wahl's factor. Now we will calculate the tau induced from this formula. So tau induced is equal to K into 8 W2 maximum load C upon pi d square. As spring is designed for maximum load, so we will take here W2. The students are generally confused as the two values of the loads are given, that is W1 and W2. So whichever is taken, so students are confused. So generally the spring is designed for maximum load, so here W2 is to be taken. So care should be taken while selecting the values of W1 is to be taken or W2 is to be taken or difference of that is to be taken. Tau induced comes out to be 323.96 Newton per millimeter, as tau induced is equal to 323.96 Newton per millimeter square, which is lesser than tau permissible 350 Newton per millimeter square. Hence wire diameter is safe, hence it is safe. Now we will calculate total number of coils from the formula delta is equal to 8W C cube into N upon G into D, or transferring the values N on left hand side and other values on right hand side. This formula becomes like this: N is equal to 1 upon 8 into delta upon W in the bracket and G into D upon C cube. Now the stiffness S is equal to W upon delta, that is stiffness. So here W, the value of which value, the question arises which value of W is to be taken. So as the delta is for the difference of load, as here delta is for difference of load, this is the figure. This is the figure of the wall in closed condition and in open conditions. So when spring is initially loaded, the wall is in closed condition and W1 load is applied, and then cam in maximum position, that is maximum lift. So spring is maximum compressed, that is load W is acting on the spring, so that the difference is known as delta, that is given, that is equal to 5. So here delta is given for difference of load, here delta is given for difference of load. So we will take W as W2 minus W1, difference of load. So stiffness comes out to be 4, difference of load, that is W2 minus W1. So W2 is equal to 100 and W1 is equal to 80. So difference is 20 and delta is 5. So stiffness comes out 4 Newton per millimeter. Now from this graph it is clear that the ratio of maximum load to the maximum deflection is equal to the ratio of difference of load W2 minus W1 upon delta, because stiffness is constant. So this ratio remains constant. So this is the maximum load, the ratio of maximum load upon delta maximum will be equal to 4 Newton per millimeter. Putting the values of delta upon W is equal to or 1 upon S. So formula becomes equal to, putting the value here delta upon W is equal to 1 upon S. that is N is equal to G into D upon 8S CQ, where S is the stiffness, W upon delta, that is equal to 4. Now from this formula, putting the value of modulus of rigidity, spring wire, stiffness and spring index, the N comes out to be 7.875. So we will take 8. Spring ends are square and ground. So N dash is equal to N plus 2, that is equal to 8 plus 2, that is equal to N is dash is equal to 10. Now from this formula, LS is equal to N dash D, putting the value of N dash and spring wire diameter, LS solid length comes out to be 30 millimeter. From this formula, as the ratio W upon delta equal to W max is equal to delta maximum, we will calculate transferring the values delta maximum on left hand side and other values on right hand side. This formula becomes like this: delta maximum is equal to W maximum upon stiffness, as stiffness is equal to 4 and W maximum is equal to 100. So delta maximum comes out to be 25 millimeter. Now free length, we will calculate free length, putting the values of solid length delta maximum. The free length comes out to be 58.75 millimeter. Now from the formula P is equal to free length LF upon N dash 1, we will calculate pitch. So pitch comes out to be 6.5277 millimeter. Here the spring, no load is there, this is the free length. Here W1 is there, valve is closed condition, and here W2 load is applied, rocker arm is tilted here due to effect of cam, so valve is in open condition, W2 load is applied. So it is clear from the figure. The graph shows is plotted between the delta and W, that is the stiffness of helical spring is constant. This is all about the problems. So in this way we have studied in this session the design of wall spring. Thank you very much. This is the end of the session. We will meet in next session.